Hello, I would like to talk about automatic differentiation, how it works, and how to implement it in Rust programming language from scratch. I want to do this for a few reasons. First, it is one of the most fundamental algorithms that is basis of modern AI technologies. Second, it is hugely underrated technology that I find it fascinating. Third, it is very easy to get started. In fact, you need only 15 minutes to write the most basic library, but it has a lot of depth to dive in if you want a practical optimized solution. Lastly, it is very well fit to Rust because it can make use of sum types and pattern matching. In other words, it is a good educational material. The key idea is to represent the expression in a graph. Each operator, addition or multiplication, forms a node in the graph. A variable is a leaf node. For example, in this expression, A and B forms an addition node, and together with C forms a multiplication. We assign a local gradient 1 to the variable we want to derive with respect to, which is A in this case. Independent variables that are not the target variable to derive with respect to would be assigned 0. The derivative of expressions will derive from its elements. In this case, the derivative of addition is simply a sum of derivative of each term. Another independent variable, c, is assigned 0. Finally, a derivative of a product is determined by the product rule that's shown below. Let me introduce you what automatic differentiation is capable of. This is a pure Rust implementation of automatic differentiation library that I wrote called RustGrad, which has a lot of examples. There are curve fitting examples, peak separation, path smoothing, and classification example. There is also GUI demo project called RustRoll, specifically contains control problems. I will not go into details of each application. However, as you can see, there are a lot of applications even without deep learning. Now, let's dive into coding. Let me start by creating the cargo project. Cargo new AD test and open the project with the editor. I trust myself, and we have an empty cargo project with hello world. Check, and it works. So now, first thing we want to do is to define the data structure. So our node is called term, which can be either a value or another node that contains a reference to subsequent node. However, it doesn't compile, as you may know, because Rust doesn't allow us to put reference inside struct without lifetimes. So we need to put lifetime here and here. And it still complains because we need generic for the lifetime. And now the term itself is a generic struct. We need to put the lifetime annotation to the sub expression. Now this is the most basic unit of building block, so we can start building the tree. Let's make a initial value, call it A, for example, and another term B, and let's make a addition of these two terms. Let's see if it compiles. Yes, it compiles. However, it's not used for anything. So let's define an evaluation function which returns F64 by evaluating an expression. And we don't need a generic lifetime here because it's elided. And we can match against the expression. And first variant we need to consider is value. And we can simply return the value. And to evaluate the addition, we need to bind left-hand side and right-hand side, evaluate each of them, and add them together. Now let's try evaluating this expression. And to debug this easier, we want to derive with debug and show the debug representation of each node. And let's see. And we have a correct result now. So this is just simple calculator. We want to add another term to make it more interesting, which is a multiply. We can copy this whole thing and just replace plus with multiplication. Now we can build a bit more complicated expression. Let's introduce a new term C and multiply AB with the C. Now we can evaluate this by eval function. Let's see. It's 3 times 42 equals 126. Okay, it looks correct. Now we want to derive this expression with respect to any of these variables. So we define a new function, derive, to do that. But we need not only the expression to derive, but also the variable to derive with respect to get the variable. So we again match against the expression. And if it was a value, we want to use the with respect to variable to determine if it's a variable to derive with respect to. In that case, we should return 1. Or if it's unrelated independent variable, it should be 0. And another case is addition. It's made of left-hand side and right-hand side. And we can derive each of them with the same variable to derive with respect to. And multiplication is a bit more interesting because it's made of special multiplication rule. If you remember calculus, a times b divided by dx is x times dA dx plus d sorry a times dB dx plus dA dx times b. So we need to encode this rule. We already have eval function, so it's trivial to evaluate a and derive right hand side as the same way as addition, and the other term derives left hand side, and multiply with right hand side. Now this is a complete expression. Let me annotate this with addition rule. Now we have this error here because Rust differences cannot compare each other. So there are many ways to compare objects, but in this case we want to compare the address of each variable, so we cast it to constant pointer. Now this should work, so let's see deriving this expression with respect to a. Let's see. So this is 42 because our variable to derive with respect to is this one, and it's multiplied by this, so the local gradient should be 42. We can try other variables like b, it's the same, and if we derive with c, it's now 3 because the coefficient of this variable is this part, which is 3. Now we can derive the whole expression, and you can imagine you can expand this method to many more terms like subtraction. Then we should have minus here, or division, and you can extend this derive function to include these rules for the various kind of terms. So this is it, and this is called forward mode automatic differentiation. And there's another way to do it called reverse mode automatic differentiation, which I will talk later. That's it for today, but I plan to cover the following topics in the future videos. Reverse mode automatic differentiation is an important technique for optimization problems, where the number of input variables are much more than the output. Tape data structure is a technique to implement reverse mode AD in a very efficient way. Dual numbers are sometimes used to compute forward mode AD without using much memory, but it has its own challenges. Higher order differentiation requires some special treatment. Tensor types, as the expression nodes, are used in deep learning frameworks such as TensorFlow, PyTorch, etc. So see you in the next videos.